right, and we're in the middle of this problem here, making our hexa-substituted benzene, and we made some decisions here. We did chlorination at the end, right? Then we reduced our nitro group, second to end thing, and then bromination here, and that's a good choice to do there because you see we've got the nitros, which are meta-directors, enforcing with the ortho direction of the isopropyl there. And then here, we just do what? Excess of nitric acid and sulfuric acid. So it's not too bad to see this product here, which is a very difficult, challenging problem, I'd say. But if you analyze it backwards a little bit and think about these, you can see how that might go on there a little more efficiently. And with the enforcing idea, you might be able to change the order of where you do the brominations versus the chlorinations. And once you propose a structure, go back through each one and make sure this is an ortho para director, that should be fine. And this is, an ortho director where the bromine goes. And then reducing that, now these are strong ortho directors, right? The strongest ones are going to go right there for the two things. So looking at that and seeing that ortho relationship there is kind of the first thing to look at. All right, make sure you do plenty of those problems, multi-step problems. There's a lot of good ones at the end of the chapter 18 there. Let's look at the sample test now. I've got the overhead up here with that. And again, if these things don't show up too well for you here, we're going to have to, Aaron, we're going to have to look up here. Okay, there we go. You're okay. So you have this document on Learning Suite. So pull it up in a separate window if you'd like as we go through the video here. But you can look at these, and I'll just point out some of the problems. And this is the solution file. Work with the regular file without the answers showing there first. And I think you can be fine. A lot of problems will just be simple definitions and single concepts things. Make sure you know the difference between conjugated and isolated and cumulated dienes. This is a cumulated diene right here, 6. The conjugated one is right here, where they're adjacent to each other. This is isolated and isolated, okay? And then resonance effects, we can ask you different things about there. All the same here, except this one, where it's got an sp2, a methylene right in the middle. So that's not the same resonance form, whereas these, A, C, and D are all related there. And then asking about aromaticity and how we can get from a non-aromatic compound here to an aromatic one. It would be loss of a proton, which would give us the anion shown here in B of 6, okay? Sometimes you can find concepts within different problems that help you out there. Nitro group classified as a meta-director due to what? Resonance electron withdrawal, right? Very strongly resonance withdrawing. Aromaticity here, which one's not aromatic, would be this one. That's 8 electrons. It's non-aromatic, it puckers, it's not planar too. This one is though, if you have the 10 electrons in there, the dianion of cyclooctatetraene is indeed aromatic. I think I pointed that out in class. These are resonance structures, A, B, and D, except this one here. Again, you have a methylene now at this position, and that's not allowing for the same delocalization as all of these. This one's kind of a tricky one, you could say. This bromonium ion is just the lone pair here interacting with the cation there. So you have to bridge over those electrons, and you're just moving electrons. You're not moving the atoms. And bromonium ions, iodonium, and chloronium ions do have resonance structures also, okay? Even though technically some people might say, well, you're making an extra bond there. Well, you're also just moving these pair of electrons into proximity to that cation, okay? So, this one is definitely not a resonance structure because you've moved the atoms. You've created a different group there at that position. Now, this is a good example here that lets you reinforce some ideas here. If you're going to brominate this compound, this ester here, which ring is going to be more electron rich? Well, it's this one over here. because the lone pairs by resonance can come in and donate on this ring. Here, this ring is deactivated because it's on the opposite side. It's next to the carbonyl, right? So these are electrons drawn out that way. So if you draw the different resonance structures, you'll see this para position right here is the choice that you're given there. We're not showing the ortho as a choice there. That would also go ortho, but the para one would be the one to go there. Aniline, yeah, remember if you're in strong acid here, it becomes a meta-director, okay? Diels-Alder, a 4+2 cycloaddition, yeah, diene with dienophile. Those are the terms you need to know there for that. Yeah, compound react slowest rate. So know the general positions of where the different groups are on that chart, that big chart with the different groups. Nitro, remember we said it's the most deactivated because there's always a plus charge on the next to the benzene. So that's always the most deactivated. Fruitocrase problem, over alkylation. I showed you that with the toluene example before. Here's an application question. Retinal in the vision process, important vitamin. Yeah, retinal there. Cumene, isopropylbenzene. Pantothenic acid, we haven't covered that. And morphine, that's an alkaloid drug. Okay, so know some of those application definitions, some of the stories that we told you. Maybe just one or two on the test, not a bunch of them though, okay. Homo-Lumo interactions, identifying here, there's a one node right here. So this is the next molecular orbital up, where they're in phase here, below, and then above. So there's a node right there. So that's the next higher one up from the ground state, lowest one. This is the highest occupied molecular orbital, where there's one node, yeah, continuous ribbon. Consistent with NMR. Now we did mention some NMR, how the aromatic hydrogens can be shifted down to the 7 range, okay? And these are different here. These two that are ortho to the chloride are a little bit further downfield than the two next to the more electron-rich methyl right there. So this is the most consistent one here with this structure, okay? And what are these right here? Oh, that's the methyl group right there. I'm not big into NMR, and I know a lot of you will get that from Dr. Bronson. Once in a while, I put an NMR question related on this test because it fits into aromaticity. So that's why we show that. Here, you have to have at least one benzylic carbon-hydrogen bond to do this cleavage with KMNO4 or chromic acid. Maybe I didn't mention KMNO4 also does this oxidation to benzoic acid. The book shows it though, and it's chromic acid or KMNO4, the other strong oxidant. Will cleave all these alkyl groups off and make all of these go to benzoic acid, but not this one. That thwarts the mechanism at that point. There's no benzylic hydrogen to pull off to get that started. The mechanism is quite complicated that way. Which hydrogen atoms are removed upon bromination? Well, it's the benzylic one, B, right? Low energy conformation of butadiene, S-trans, okay? Not aromatic because it's not planar. These two hydrogens point at each other, so they get away from each other. That puckers that molecule away from planarity. Analyzing Diels-Alder, so you can see here you've got the ester and this methyl group here, trans to each other, and there they end up right there. And so we need a diene over here that has this methoxy on it, and there it is right there. So C is the answer there. And then on normal write-on tests, we have a sheet of reactions here. So we have to switch these over to multiple choice type problems now. But yeah, we can give you starting materials and conditions, and then you have to come up with the right product. And a common one are these 1,2 versus 1,4 addition. So if we're at low temperature here, well, we get the 1,2 product being the kinetic product, okay? Not the 1,4 product. And then we got sulfonation, we got Diels-Alder, Friedel-Crafts alkylation, but this one, remember, goes with the shift. If we try to coordinate here, that'd be a primary carbocation. It migrates over and we get the isopropyl products, okay? Diels-Alder here to give the norbornene product with cyclopentadiene, and that's the endo product down underneath by the diene. So this is an example where you need to apply the endo rule. And here we're chlorinating a deactivating group, so that's what, a meta-director. Okay. Then we're brominating here, chlorobenzene, that's an ortho-para-director, and it's slow. Okay, but because of the lone pairs on the chloride, we still get ortho and para products. Okay, and then there's another way to ask these reactions. We can ask you to provide the reagents for a reaction, or we can ask you to provide the starting materials. Okay, there you got to analyze what the product is and what those conditions were, and what else was needed. Well, benzene. Okay, that's an easy one. And how about here? Well, this is what, the Clemenson, and that would come from this aromatic ketone, right? Put the two hydrogens there. Diels-alder here, we need this cis cyanoalkene because the cis relationship there. Okay. Then we chlorinate, what's this again? That's acetophenone there. It's a meta-director, and those are the conditions for chlorination. Yeah. What about this one? Oh, NBS and light, and then potassium t-butoxide. Well, we need to, take an ethyl, aromatic ethyl there, brominate the benzoic position, and then E2 elimination to form the styrene. And let's see, here we've got higher temperature HBr, and we're adding to form the allyl bromide like this. And notice that's a disubstituted alkene right there. So what, that would be the thermodynamic 1,4 addition there. That we'll have to pick conditions. So the proton will go on the end, and then the nucleophile goes on the end also to give the alkene more substitution. And this is nitration and reduction. Pretty straightforward. Now these harder write-on problems, we can ask about little tricky parts of mechanisms and things, multiple choice here. Obviously, we can't set up a big problem that requires multiple concepts to come together. But we can ask about, tricky parts about mechanisms and things like this. So this involves over-alkylation and then converting this trimethyl product into the 1,3,5-trimethyl product. And you're told that after a longer time and treatment with more acid, eventually this isomerizes over. So this is the kinetic thing that comes out of over-alkylation. Of benzene with excess, these reagents here. But this one can be treated longer with more acid, and it'll actually switch over to the all-meta product. Now, we didn't show you how that works, but you need to come up with a mechanism to convert this into that. And you do it by putting a proton back on there, and then shifting over, and then losing the proton again. And this, you see, gets all the methyls as far apart from each other as they can. This initial kinetic product has two of the methyls ortho to each other. So this one is a little more stable in the ground state. And this is how you get to it to avoid the steric thing here. It relieves the strain. So when you see the full answer to it, it might begin to make sense. But the tricky part here, this problem, when we did give this, and we did give this as a problem on a test, you've got to come up with this mechanism. But we talked about how you can reprotonate benzene rings when we did the sulfonation reaction. So that's kind of like that loss of the sulfonic acid off the benzene ring. But here it goes back, and then the shift occurs to avoid the steric clash. Anyway. And then, we can do multiple choice questions with multi-step thing, where we give you some choices of which different reagents to use in a multi-step thing. Here you're asked to make this compound right here from benzene. So you want to nitrate first, then chlorinate, because you see the amine and the chloride are meta to each other, but you need to use the nitro to give that meta-directing effect. Then you can reduce it to the aniline and then brominate, like we did on that harder problem. There it is right there. And it's kind of recognizing these two bromides are in the ortho and the para position relative to the aniline nitrogen. That's a little bit trickier one, but I think it's a good problem there. But yeah, we could switch that one pretty easily over to a multiple choice. This one just involves more details, analyzing from the frost circles why this compound is aromatic. And so here's the frost circle on its edge there with the corner at the bottom, and then you can imagine the circle there. And you see the 6 orbitals there are below the halfway point. And in this anion, that's the 6 electrons right there in those molecular orbitals. Remember, the frost circuit just tells us what the molecular orbitals might look like. You have to, change the shading, everything, and do the nodes here. There's 2 different ways to have one node in this structure. That's what it says. But you can apply this and just go through this. 6 pi electrons, 4n plus 2 rules, okay. It's planar. You can say that's why it's stable. The cation, though, has the 2 electrons here that are half filled. They spread out then. And if you half fill molecular orbitals, it becomes diradical in character, and that's an anti-aromatic effect. So that's less stable then if you have the 4 electrons. If you have them all filled below the halfway point, then it is aromatic. But if there's other issues, then it's not. Here's these worksheet problems. So these weren't problems on that test, okay? That sample test was an actual test years ago. The worksheet is just a collection of harder problems to give you some extra practice using multiple concepts. Things that are a little trickier. So here's the full MO discussion for hexatriene, which is the 6-carbon polyene with 6 atomic orbitals. We then need what? 6 molecular orbitals. And we follow the same way through here. Here's the filled ones with what? No nodes, 1 node, and then 2 nodes. You see the shading there? And then going up, this is what? 3 nodes. You see where the dashes are? 4 nodes, and then 5 nodes. These are all the empty orbitals, okay? And then resonance structures, this is okay. You can just abbreviate. We won't ask you to overanalyze something, but with this harder problem, there's a lot of resonance structures here. You can kind of see how we push them around there. This is a little bit harder problem from the worksheet. I went through this discussion on the worksheet there. The kinetic product is always the one where the nucleophile goes with the more substituted cation and gives the less substituted alkene. Thermodynamic product always gives the more substituted alkene product, okay? This Diels-Alder here, you have to analyze the Regio selectivity. We did that. We showed you how to look at the different resonance structures and decide which end of the diene and the dienophile should come together. And then applying the endo rule, that's the main product right there where they're cis to each other, actually. So those aren't necessarily harder. Some of these are examples I use in class there. So let's see this worksheet, aromaticity. Yeah, if we do solvolysis here, SN1, we've got to ionize. Non-aromatic allocation. Aromatic, there's tropylium cation. That one's the fastest. Why? Because it's aromatic. So that transition state for the ionization is going to be lowered. Okay. This one's anti-aromatic. That'll be the slowest one for SN1. That won't even give SN1. This one will quickly give SN1, is this one also. But yeah. Again, you got to apply the reaction from 351 and then the aromaticity effect of the solvolysis. That one's a little trickier. Here's an NMR one, which is interesting on phenol. You're given these shift values here, and based on your resonance structures, you can kind of see which hydrogen will be next to the more electron-rich anion-like thing in the resonance structure. So push the electrons in here. You can have anion here or over here, but never there or there. So that makes the shifts a little bit further upfield. They're a little more shielded, we say. That's the differences there. This one, the meta position, they're never next to the anion, and they're similar in shift to benzene, 7.3 ppm. PK one, I like this one. Trinitrophenol. It's also called picric acid. And that pKa right there, you're told, is 0.4. For phenol itself, the pKa is 10. So why is the trinitrophenol so low, so much more acidic? Well, it's because when you take that proton off, the conjugate base becomes more stable, right? Because you have many more resonance structures out onto the nitro. And by the way, it is a detonation hazard like TNT. Picric acid is explosive material. And then we have, some choices here. Where are you going to put on the electrophile here? Well, you go with the strongest donor, and that'll be aniline here with the lone pairs like phenol. Can donate there at that ortho position. And that para position's also open. That'd be your fastest one. Your next one is what? This one? Because of the no, that's also slow because of the nitro. Next one here because of the alkyl. That's a withdrawing group also, but it's a mild deactivating group. These others strongly deactivating. That's a strong deactivator too. Remember, we told you the strongest deactivator is nitro. So that's one to keep track of. Here's a mechanism we did not cover in the chapter, but you can apply the principles and figure out how this reaction works. Of course, I'm not going to give you a bunch of reactions we haven't covered. So this is a hard problem, but you apply the principles here, protonate, the carbonyl, and then attack. Here's your true electrophile for the electrophilic aromatic substitution with a new electrophile, though. That's why this is a little tricky. Once it goes on, we got to lose the proton like before and get to that. Then we can protonate again, lose this, form benzyl cation. That's a resonance stabilized cation. And then chloride, a weak nucleophile, can go on there. And you can form the chloride. Okay. So we saw that before. Alcohols can be halogenated in 351 if you treat it with HCl or HBr, right? So this part is just like from 351. This part here is the new electrophile. And then the multi-step ones here, I kind of went through some examples similar to these. So you can work these on your own at first, then figure that out. Anytime you see a styrene in a product, you got to do this benzylic bromination, the radical thing, and then the TB-toxide to eliminate it there. And here we got Friedel-Crafts acylation and alkylation. These others, I think you can see, here's this one with the desulfonation at the end to get the better selectivity there. And yeah, this one's not too bad if you look through it there. So let's see. I think that's it. Yeah. Zoom into office hours. We can help you out before the test, of course. And recitation. We'll be helping you out there. But again, use the sample test wisely and help yourself out there. Very good. We will see you next time. Good luck on the test. Very good.